Good morning, students. Welcome to Sri Guru online classes. In the last class we discussed modulus of elasticity with the help of stress strain. Today we are discussing that stress strain of a different materials that causes in the form of fractions or fracture point or breaking point. We are going to discuss that particular limit of elasticity, that elasticity on the basis of applied force. Let us consider this is the rigid support. This is the rigid support. Here we hang a spring and the spring is a mass holder. The initial spring length is L. After adding a mass on this span, definitely length of the spring goes on increases. This mass we are considering in the form of stress means stress strain. With respect to stress, we are identifying the strain values. Just to discuss these things in detail. Here it shows the reading on this particular scale. In the scales we are going to see the values with respect to a certain mass. We applied a stress initially, 0 stress, definitely the strain on that particular body is also 0. Let us consider by the spring. Listen here, same type. Listen here, this is the mass holder. We applied a continuous mass on this. Definitely the spring is going to increase its length is going to increase. Again we add a mass, definitely it is also going to increase the length. We applied a stress continuously, we applied a stress. If suppose this mass or this force we are going to remove, definitely it will come back to its initial state. This is the development of restoring force in that particular spring. Initially its diameter is more, but after applying a force the diameter goes on decreasing. This diameter decreases means length increases. Why? Because we are applying a force in the form of mass with respect to acceleration due to gravity. Force is equal to m into g. We applied a mass in a such a way that is at a particular limit the spring is going to stretch. The permanent set is going to develop on this spring, that is not going to regain its original shape or size. This is already we discussed in the last class. In the today class, with the help of curve, we are going to identify the strain on a particular that spring. If we applied a mass 5 kg, we are going to see the change in length. Here is strain means delta L by L. Stress means force acting per unit area. Here shall I considering W? Why W? Work, or let us consider this is force only. Force acting per unit area. Force acting per unit area. Stress means force acting per unit area. With respect to this mass, let us consider here is 2 centimeter, 3 centimeter. We are seeing on that particular meter scales. This observation by using a curve or by using a graph, we should represent the value of stress. With that respect to that value of stress, we are going to identify the strain values. At a particular limit, that strain causes plasticity. From elasticity to plasticity, it is going to convert. Let us consider. Along y-axis, here is stress applied, here is strain. Initially at origin the stress is 0, strain is also 0. We applied a stress at this particular layer. Definitely the strain is also acting at this particular point. Again we applied a stress up to this. Again at a particular point it is going to strain. Particular point of strain. Again the particular point of strain. Again we increase the stress. The strain is also increases strain. We are continuously we applied a stress. The strain is acting on that steel material at this particular layer, at this particular point. At this particular point we applied a stress with respect to strain is developed on that particular body. Here applied force in the form of stress, the unit changing in this particular region from, let us consider this is the origin and this is the point A. Up to this point the variation of strain per unit is same. The variation of that steel per unit is same. If suppose by applying a force 5 kg, here the length is 2 centimeter. 10 kg, the length is also 2 centimeter only. Uniformly, or stress is directly proportional to strain. Stress is directly proportional to strain. At per unit values, the stress applied, the strain is also same. Why? Because within this limit from 0 to A, which obeys the Hooke's law. O to A point, a material which obeys the Hooke's law. Beyond this point, the material is not going to obey Hooke's law. Let us consider a B point. This is our A point. Up to this point, the material which is perfectly elasticity that obeys the Hooke's law. Beyond this point, we applied a stress applied continuously. A very small stress is acting on this particular steel rod or steel wire or any steel spring. We applied a small stress, a very large strain is developed on this spring. Up to this point is also the body is going to regain. The body is going to regain its original position. Beyond this point B, if suppose we applied a stress, let us consider C point. At this region we applied a stress, it is going to change as plasticity. The change as plasticity, this we called as permanent set. This we called as permanent set. This we called as permanent set S, and this is the origin. At C point, there is no regaining capacity that is fixed, which is not going to regain its original configuration. Why? Because this is our original. This much of length is lagging. Why? Because it is going to convert from elasticity to plasticity. Between this region, it is a perfect elasticity and also it obeys the Hooke's law. In this reason also, the material which regains its original shape or size after removal of deforming force. But beyond this point B, we applied a stress. Definitely that material is going to convert as plasticity, and this point we called as yield point, or this is called as elastic limit. This is the last point, that is elastic limit, or we can also call as yield point. And this C, already I explained, this C is called as permanent set. Permanent set means which is not going to regain its original shape after removal of that stress. It is not going to regain its original configurations. Again we applied a certain stress on this particular steel rod. The strain is developed. Let us consider that point is D. A small stress is applied, very large strain is developed on this particular steel materials, and which is converting as a ductile materials. Initially this is up to this is elasticity, now it is plasticity. After conversion of elasticity to plasticity, we applied a stress, very large stress, which is going to cause or which is going to break a materials. Very small stress means brittle materials. Very large stress is acting on that particular body, we call as these type of materials is called as ductile materials. And also this point is called as breaking stress. Breaking stress. And if we increase the stress once again at this particular point, last point, that is fracture point or breaking point. In this particular graph, we are going to identify, this is our initial length of that steel rod, that is L. We applied a stress, it is going to increase at this particular point A. If you release that stress means it come back to its original configuration or original length. This is our change in length delta L. If you release this stress, definitely it will come back to original state. Again we applied a stress at this particular point B. Up to this also it is going to regain. But beyond this point, if we apply a stress, it is not going to regain. This is converting as plasticity. Again, this is also large plastic range, that is D. Up to this point, it is going to break. We applied a stress on this particular steel rod, it is going to change. From this point, it is going to convert, or it is going to change from elasticity to plasticity. It goes on. If we applied a stress, the strain is going to increase. A small stress is increases, strain is very large. Continuously we applied a force on this, the length is goes on increases, By this tabular form, we are going to mention the values 5 kg, 10 kg, 20 kg, 100 kg. We are increasing the force. Again, we are seeing the change in length with respect to original length by using this stress strain curve. Here, from O to A, this is called as, what do we call it? Which obeys Hooke's law, and B point is called as elastic limit, or yield point, up to this region the material is going to regain its original configuration. It come back to its original state after removal of deforming force. Beyond this B point, or you just consider beyond this B point, it is going to convert as plasticity, and this C point is called as permanent set. This is permanent set, and this D point is breaking stress. What is breaking stress? The maximum stress we applied on a materials which causes the breaking of that particular materials. This is the graphical explanation of stress strain curve we can identify, and this we can done in the laboratory also. You have a particular experiment in the first year. We are going to do this experiment in the lab. Okay, listen here. This is elastic limit, this is plastic limit. Up to this region the material is not going to break, and up to this region is also the material is not going to break. These type of material we call as ductile materials. What is mean by ductile materials? Even that material is plastic materials, behind that elastic limit we applied a stress. It is not going to break immediately. Behind very large stress is going to applied. Very large stress is applied beyond the elastic limit. That material is going to break. That type of material we call as ductile material. We can say that copper, iron, etc. We can say that these type of material, even though these materials which is going to convert from elasticity to plasticity, that materials get a particular amount of strain by applying a large stress. The material which is going to break after certain amount of stress, it is going to break. Very large stress is going to act. Another material is there, that is brittle materials. Very small stress is going to act, even though that after the elastic limit we applied a small stress, that material is going to break. This type of material, cast iron, we can say that one more. This chalk is also a cast iron, we can apply chalk. Listen here, it is very small stress we applied on this chalk, means it is going to break. These type of material we call as brittle materials. We can consider many examples. And in the last class we discussed the elastomers. Elastomers means the material which does not obey the Hooke's law. This type of material we call as elastomers. Okay. Okay, this is about the stress strain curve. Listen here. In plastic material, there are two types of plastic materials. First material, that is ductile material, which shows very large plastic range. Which shows very large plastic range. Very large plastic range beyond the elastic limit. For example, iron, copper, silver, etc. These type of material which shows a very large plastic range beyond the elastic limit. That type of material we call as ductile materials. Brittle material. Second one is brittle material. Very important material in the plastic. Okay, here ductile means which shows the very large plastic range. Brittle means which shows very small plastic range beyond the elastic limit is called as brittle materials. And last one material type is, that is elastomers. Already we discussed in the last class. What is this elastomers means? Which does not obey Hooke's law. Which does not obey Hooke's law. Listen here. This is our elastic limit. Behind this elastic limit, this material is going to convert as plastic, which shows very large plastic range. That is called as ductile materials. Which shows very small plastic range. That type of material we call as elastomers, which does not obey Hooke's law. Beyond point A, these materials which does not obey, even though up to B it is elastic materials, but this point or this region we call as elastomers. Why? Because in this region, particular region, it is not going to obey Hooke's law. Stress is not going to proportional to strain in this region. That's why this region we can't say that stress is directly proportional to strain. This reason we can say that elastomers. Elastomers, example is for elastomers is rubber, or we can also considering as wax, etc. Okay, example for brittle is, just to consider this chalk is also brittle materials. Why? Because very small stresses we applied on this materials, it is going to break. Chalk or cast iron, etc. we can consider. After the conversion of plastic, that is going to break immediately. This type of materials we can see after the elastic property of a materials. A material is elasticity, no doubt. After applying a continuous stress on that particular materials, that materials loses its strength. Because of losses of strength, these type of materials we can identify, which shows very large plastic range, that we call as ductile materials. A material which shows very small plastic range, that type of material we call as brittle materials. And the material which does not obey Hooke's law, those type of material is called as elastomers. And last definition is elastic fatigue. Elastic fatigue. What is this elastic fatigue? Here we are applying a continuously stress on this particular steel rod. We are applying a continuous stress on this particular steel rod. Because of the stress, the loss of strength on a material due to continuous stress is called as elastic fatigue. Loss of strength or continuously acting on a material. What is going to act? Stress. Continuous stress is going to act on particular material we call as elastic fatigue. Very important definition. These are the very important definition. They may ask in 1 marks or sometimes they may ask in CET also. Which type of material shows the very large plastic range, and which type of material shows the very small plastic range, and which type of material which does not obey Hooke's law. If we suppose we apply continuous stress on the materials, what is going to cause? Elastic fatigue, the loss of strength of that materials. These are the very important definitions. Now, the very important derivation they may ask in 3 marks bit, that is Poisson's ratio. And up to this we are going to discuss about the length, area, volume. We never discussed about the diameter. In this Poisson's ratio we are going to discuss Poisson's ratio. Before going to explain in detail Poisson's ratio, the statement for Poisson's ratio is it is the ratio of lateral strain to the longitudinal strain It is the ratio of lateral strain to the longitudinal strain. Already we know that. What is this longitudinal strain? Change in length by original length. We know that already. Change in length by original length. We should know about the lateral strain. What is this meaning of lateral strain? Lateral strain means, till today we discussed about the length, area, size, volume. We not discussed about the diameter. Just you consider this is the cylinder. This is the initial length of this cylinder, and this is the initial diameter of the cylinder D, and this is the length of the cylinder. We applied a force on the cylinder. Definitely it is going to increase its length, goes on increasing. This much of length goes on increases. This is our initial length, and this is length we called as, already we know this, that is change in length. But as compared to this diameter is going to decrease. As length increases, diameter decreases. Why this diameter goes on decreases? Here we applied a force. Because of this force, the length increases, diameter decreases. What is the meaning of strain? Change in diameter to the original diameter change in diameter by original diameter is called as lateral strain. Longitudinal strain means change in length with respect to original length. Similarly, here lateral strain means change in diameter to the original diameter. Now, what is the statement for Poisson's ratio? Lateral strain by longitudinal strain. Lateral strain by longitudinal strain. Lateral strain by longitudinal strain. The Poisson's ratio denoted by delta, that is lateral strain by longitudinal strain. Longitudinal strain. Here lateral strain means change in diameter. Just to consider change in, this is the initial diameter d, or just to considering small d or capital D, it's left to you. According to NCERT means this is the small d and change in diameter is delta d. Change in diameter, that is delta d, or you just to considering capital D, it's left to you. Change in diameter to the original diameter. And we know that longitudinal strain, that is change in length by original length. This we can write, change in diameter by original diameter is called as lateral strain, that is delta d by small d whole divided by delta L by L. Here this is the initial diameter, now this is the change in diameter. Change in diameter means definitely it is going to negative. Why this negative sign? Negative sign indicates that decrease in its diameter. Decrease in its diameter. We can write like this, minus delta d into L whole divided by delta L into d. This is the expression for Poisson's ratio. And this Poisson's ratio helps to find the change in its diameter after applying a certain stress. If we acting a stress continuously on this solid bodies, that solid body's length goes on increases. This length causes in diameter, that diameter is decreases. That's why this negative sign indicates decrease in its diameter. Decrease in its diameter. And the Poisson's ratio is between -1 to 1.5. These are the numerical values, and by practice we are considering from 0 to 1.5 for all elastic materials. The values is between 0 to 1.5. Listen here. If they asked in 1 mass, what is the SI unit for this Poisson's ratio? What is the definition for Poisson's ratio? Lateral strain by longitudinal strain. Lateral strain, change in diameter by original diameter. Diameter in terms of meter. Original diameter, that is also meter. Length in terms of meter. Original length in terms of meter. These are going to cancel. We can say that Poisson's ratio, no unit. And also lateral strain or longitudinal strain, any type of strain not have any units. It is nothing but a number. We can mention in terms of number. In some of the exams they are going to ask by graphically. Let us consider first graph. This is the first graph, stress versus strain. stress versus strain. They mention graph like this. And second one is stress, strain, and this graph they mention. And out of these two graphs, which is more elastic and which is less elastic, they are going to ask. More elastic means which obeys Hooke's law up to particular regions. Up to particular regions, the stress is directly proportional to strain. But here is, this is also linearly increased, but at this particular region, sudden increase of stress, sudden increase of strain. Again, sudden increase of stress, sudden increase of strain. These type of materials we called as, what we called? The loss of strength of materials immediately, that we called as ductile materials after elastic property, which is going to convert as plasticity, and per unit value is goes on increasing, and we can't say that this is the elastic materials, this is ductile materials, which shows the very large plastic range. Up to this is going to break. Or sometimes they may ask which of the following is steel property and which of the following is rubber property. Rubber, if we applied stress, means definitely it is going to strain immediately, which is not going to come back to its original state. But steel, which is going to come back to its original state after removal of stress, this obeys the Hooke's law, and which is not obeys the Hooke's law. And this is the today class. We discussed about the stress strain curve, Poisson's ratios, and the graphical representation of ductile and brittle materials. In the next class, I am going to discuss elastic strain energy and also some of the applications of elasticity. Okay, thank you.